Next, I want to look at DC magnetic simulation. We investigate the induced magnetization, which would be relevant to magnetic particle inspection or magnetization mapping. In this particular problem, I have XY symmetry. This is the air region. The flaws here have the permeability of air. This is a steel bar now, and the steel has a permeability of 100. I'm going to zoom in a little bit farther so we can see the magnetization coil I've specified with vertex labels. Okay, this is the left coil, this is the right coil. Okay, I've given a linear current density of -1, actually total current in the left coil, and a right coil has a linear current of 1. I've specified a test point here, which we can monitor using label mover and scan this as we have before, and we can see the DC magnetic field due to defects in the conductor here, or the magnetic material. So we'll just look at the field distribution. And this is the DC magnetic field, DC magnetics. You can see that the DC magnetic field is going to be perturbed by the presence of any defects. I want to illustrate the ferrite needle concept for improving the spatial resolution. This is the same as the previous simulation, except I've included a ferrite needle above the permeable sample. So this would be our magnetization coil that is on each side of the ferrite, and once again the vertex labels, the left coil, this is the right coil. Our sensor now is located on the top of the ferrite needle. This is the air region. There's actually a flaw in the conductor here, and I'm sorry, it's a ferrite. And the mu metal has 10 to the 4. Once again, the steel. And we'll just look at the field distribution. We could scan this with label mover. I want to illustrate how the flux is channeled up the ferrite needle. So if we had a sensor here with poor spatial resolution, we could prove that since a small flaw being scanned under here will have changed the total flux that's being channeled up through the ferrite. We can make a magnetic field plot, various quantities such as the energy density. Okay. Flux density. Vector potential. Finally, I wanted to look at the stress distribution near defects in aluminum samples, both considering external loading and also thermal expansion. So this is done in the stress analysis module of QuickField. By the way, we can combine stress analysis with the various models such as magnetostatic and electrostatic modules. So the sample under the test here is a aluminum bar. Now, aluminum has a Young's modulus of about 68 gigapascals, a Poisson ratio of 0.3, shear modulus about 1/3 of the Young's modulus. We are in Cartesian coordinates. This is XY symmetry, so we are looking at this is a planar geometry. The crack I'm simulating with a region with 0 Young's modulus. Now we have to label the edges, at least 2. The bottom edge, I'm assigning a 0 Y displacement, so it's as if this plate is clamped along the bottom edge, a 0 Y displacement. We could also assign the normal pressure and surface force. The side, I'm assigning 0 X displacement. And on the top of the model, I'm describing a force that's acting in the Y direction of 1 Newton per square meter. So this is like a sample in a tensile testing machine that's being pulled upward here. Now we can look at the stress distribution. It's already been solved, but I resolved it here. Now, what's this showing is the deformed boundary as we're pulling our sample up, and we look at our field picture properties. The deformed shape is times 3 times 10 to the 10, so we can actually visualize it. We wouldn't be able to visualize the actual displacement here, so this has been multiplied by a scale factor. We're looking at a color map of the von Mises stress, and this shows the maximum and minimum values of the von Mises stress. Alternatively, we could look at the Tresca, the Moore, and the Prager, and you can see that these have very similar maximum and minimum values here. The most popular is the von Mises. And the maximum stress is occurring here at the edges of the defect, which would tend to propagate this flaw under loading. Now we can also compare, if we go back to our aluminum, the load here, the aluminum has a coefficient of thermal expansion. Here I've assigned initially a change in temperature of 0. So I want to investigate the stress distribution under a change of temperature of 10 Kelvin. Now I'm going to remove the external loading from the top of the model and resolve. Okay. Now the model appearance here is because the stress distribution is very nearly 0 in this region. In fact, the stresses under thermal expansion are much less than the stresses that you encounter under external loading for this particular geometry and flaw. So this concludes the simulations today using QuickField for NDT. You can see more simulations here in the textbook, and also coupling thermal analysis and stress analysis using the defect-free approximation. If you have an unperturbed eddy current density, you can calculate using the Biot-Savart law the flaw response for various probe geometries and so forth.